Recall that the equation of the unit circle is x squared plus y squared equals 1. So if I want to check to see if a point is on the unit circle, I can just take those x and y points, plug them into the equation, and if I get 1, I'm on the unit circle, and if I get anything else, my point is not on the unit circle. Also remember that the unit circle is made up of infinitely many points. Even though there are those 16 that we study closely, there are many other points aside from just those. So in problem 1, we're going to ask if the point -7 over 8 root 15 over 8 belongs on the unit circle. So we'll just plug those numbers in. -7 over 8 squared plus root 15 over 8 squared, and check to see what we get. I get 49 over 64 plus 15 over 64, which is 64 over 64, which is 1. So yes, this point is on the unit circle. Since this point lies on the unit circle, we can use the x and y definitions for sine, cosine, and tangent, along with secant, cosecant, and cotangent, to solve part B. Again, this part is only because we found that our point does in fact lie on the unit circle. So sine of alpha, we know should be the y value, which is square root of 15 over 8. Secant of alpha should be 1 over x, which is -8 over 7. Cotangent of alpha should be x over y, which should be -7 over 8 divided by root 15 over 8, which is -7 over root 15. And that rationalizes to -7 root 15 over 15. Problem 2, asking if the point -1/3, -2/3 is on the unit circle. Well, we can see that if we add 1/3 and 2/3 together, we get 1. But be careful, because that is not the equation of the unit circle. In order to check, we really need to have -1/3 squared plus -2/3 squared, which gives 1 over 9 plus 4 over 9, which is equal to 5 over 9. And 5/9 is decidedly not 1. So this point is not on the unit circle. That means when we try to answer those same questions, finding sine of alpha, secant alpha, and cotangent alpha, we cannot use the x and y definitions that we have from the unit circle, because this point is not on the unit circle. So instead, we should create a reference triangle. So both my x and my y values are negative, which means my point should be somewhere in the third quadrant. Say we label that point. I'm going to set up my reference triangle so that it exists in the third quadrant, and then I'll label some of those sides. I know that the horizontal leg should be -1/3, and the vertical leg should be -2/3. And then there's a missing hypotenuse, but I should be able to solve for that. And in fact, I kind of already did. From the work I did above, I know that c squared should be equal to 5/9, which means that c itself should be the square root of 5/3. Now from this triangle, I should be able to find sine of alpha, secant alpha, and cotangent alpha. Sine of alpha is opposite over hypotenuse, which means I'm looking at -2/3 divided by square root of 5/3, which rationalizes to -2√5/5. Secant of alpha is hypotenuse over adjacent. So √5/3 divided by -1/3 simplifies to -√5. And cotangent of alpha should be adjacent over opposite, -1/3 divided by -2/3, which is +1/2. Let's imagine an angle that's in quadrant 2. Like this angle right there. Now, if I were to measure the actual angle that in standard position that's going to put me over there, that's going to be this blue angle right here. Let's call it theta, because we like to call lots of angles theta. But if I wanted to look at the triangle that this angle creates, the most convenient triangle to look at is going to be this one drawn here in purple. And notice that the angle theta, if I measured in standard position, that gets me this angle, this triangle, is not an interior angle of the triangle, because that angle would instead be this guy, drawn in red. Which means that oftentimes when we're looking at angles as they exist in the coordinate plane, if we want to break that down into a triangle, it's oftentimes easier to talk about an angle that is related to our original theta, but isn't exactly theta. Because I'd like to have an angle that's inside of that triangle, an interior angle of this triangle. So we give a special name to that angle, the one that is inside the triangle that I want to talk about. We call that the reference angle. So these reference angles are always going to be measured from the x-axis to my angle in standard position. I'm always going to choose the closest x-axis to wherever my angle is. A direct result of choosing my reference angle this way is that a reference angle will always be acute, meaning it's always between 0 and 90 degrees, so it will always work out to an angle that exists in the first quadrant. And if we're in radians, that means that my reference angle will always be between 0 and pi/2. I also won't ever have any negative reference angles, because again, I want it to be between 0 and 90 degrees. So here we have angles drawn to the third and the fourth quadrant as well, with those reference angles that are labeled. So notice in quadrant 3, that reference angle is measured from the negative x-axis going down. And in quadrant 4, we're back to measuring the reference angle from the positive x-axis. Each of those reference angles are drawn in red, while the original angles are drawn in blue. We'd like to be able to calculate a reference angle based on any angle that we're given, but because of the way that they're measured, that equation is going to change depending on the quadrant that we're in. So in quadrant 2, that reference angle is going to be the difference between pi, which is straight left, and the angle that we initially started with. So pi minus theta. In quadrant 3, this time our angle is extended past pi, but we're still measuring our reference angle from straight left, from that negative x-axis, which has a measure of pi. So similar to the equation for quadrant 2, this time because theta is extended past that x-axis, I've got too much. So I want to take pi away from my angle this time in order to get the reference angle. And in quadrant 4, that reference angle makes up the difference between a complete circle and my angle theta that's given. So 2 pi minus theta. Lastly, if we're in quadrant 1, the reference angle is just equal to theta. Putting what we know about reference angles into practice, if I'm looking for the reference angle to 78 degrees, which is already in the first quadrant, that reference angle is just 78 degrees. 271 degrees is in the third quadrant, so I'll want 360 minus 271, which gives 89 degrees. For part C, I have a negative angle, which means I'll first want to get its positive coterminal angle, which is 150 degrees, which puts this angle in the second quadrant. So I'll take 180 minus 150 and get 30 degrees. .480 degrees is larger than the unit circle, so I'll want a coterminal angle that lies between 0 and 360, which should be 120 degrees, which again puts us in the second quadrant. So 180 minus 120 gives 60 degrees as that reference angle. Switching to radians, 15 pi over 8 is in the fourth quadrant, so I'll want 2 pi in the form of 16 pi over 8 minus 15 pi over 8, which works out to a reference angle of just pi over 8. 11 pi over 9 is in the third quadrant, so I'll want 11 pi over 9 minus pi, this case in the form of 9 pi over 9, to give a reference angle of 2 pi over 9. 7 pi over 10 is in the second quadrant, so I'll want to take pi, this time in the form of 10 pi over 10, and subtract 7 pi over 10 to get a reference angle of 3 pi over 10. And for the next two problems, these don't look like our typical radian measure angles, which tend to have pi in them. But anytime we have an angle with no units listed, we should assume that it's a radian angle. Because if it were an angle in degrees, it should have a degree symbol. Neither of the next two parts have a degree symbol, so these are both angles in radians. So 4.5. I know that 3 pi over 2 is right about 4.7, which means that this angle is in the third quadrant because it's a little less than that, meaning that my reference angle ought to be 4.5 minus pi. And since we're looking for exact answers, I will just leave my answer here, because this is the most exact answer I can get. Now an angle of 3.2 radians, just a little bit more than 3.14, so it's a little bit bigger than pi, meaning that this is also in that third quadrant. So I'll use 3.2 minus pi again. And that is an exact answer. Relating this idea of reference angles back to the unit circle, there is another handy way to relate these reference angles to some of the things that we're trying to memorize. So earlier I talked about specific classes of angle, like I'd talk about the pi over 6 class of angle, or the pi over 4 class of angle, or the pi over 3 class of angle. What I mean by that is that each of the angles that is in that class has the same reference angle. So if I talk about the class of pi over 6 angles, highlighted here in green, each of these 4 angles has the same reference angle of pi over 6. I can find pi over 6 right here in the second quadrant. I can also find it right here in the third quadrant, and here in the fourth quadrant, measuring each of those pi over 6's. One particularly handy property of reference angles is that my angle theta and its reference angle have the same absolute value for x and y. Same absolute value for sine and cosine, and by extension, tangent and cotangent, secant and cosecant. So if we look at the x and y coordinate for each of these angles that have the same reference angle, I have the same coordinate every time, just potentially with negatives added to either the x or the y. I can see the same thing with the pi over 3 angles. All of the angles with a denominator of 3 have the same reference angle of pi over 3, and they have the same pattern to their coordinate point. Each one goes 1/2 and then square root of 3 over 2. I'm just assigning the appropriate negatives based on which quadrant I'm in. And the same thing shows up for all the over 4s. Every pi over 4 angle has a reference angle of pi over 4, and the x and y numbers are the same, just with the appropriate negatives added depending on the quadrant. Problem 4, determining the quadrant of an angle based on the sine of 2 trig functions. So let's talk about those 4 quadrants over here on the right. So in the first quadrant, both x and y are positive. And in fact, every trig function is going to be positive in that first quadrant. Moving into the second quadrant, we have negative x values, which means that cosine is going to come out negative, as well as tangent, which is the ratio of y to x, will also come out negative. But sine, which is just going to be the y value, is still positive. Into the third quadrant, both x and y are negative, which means both sine and cosine are negative, but tangent, which is x divided by y, has a double negative, making tangent back to positive in the third quadrant. Into the fourth quadrant, we have positive x values but negative y values, making cosine positive but sine negative, and tangent also being negative. So there's a handy acronym for remembering that. And that's this ASTC, which I've frequently heard is all students take calculus, or sometimes all students take chemistry. There are a few other acronyms, so feel free to get creative if you like. But the trig definitions we'll need to remember is all sine, tangent, and cosine. And this will tell us which trig functions are positive in which quadrant. All the functions are positive in quadrant 1, only sine is positive in quadrant 2, only tangent is positive in quadrant 3, and only cosine is positive in quadrant 4. Now, these positive and negative identities also apply to the reciprocals to each of sine, tangent, and cosine. So in quadrant 2, cosecant is positive in addition to sine. In quadrant 3, cotangent is positive in addition to tangent. And in quadrant 4, secant is positive in addition to cosine. So let's put all that into practice. Part A, sine is negative and tangent is negative. Well, sine being negative means that I'm either in quadrant 3 or 4. Tangent being negative means I am either in quadrant 2 or quadrant 4. Those two pieces overlap only in quadrant 4, which means that angle delta must be in Q4. Part B, cosine is negative and tangent is positive. Well, cosine being negative means I'm somewhere on the left half, so either quadrant 2 or 3, and tangent being positive means I'm either in quadrant 1 or 3. Those two pieces of information overlap only in quadrant 3, so that must mean that angle beta is in quadrant 3. Part C, secant is positive and tangent is positive. That's going to happen only in quadrant 1. Anytime we know multiple things are positive that aren't just reciprocals of each other, we must be talking about quadrant 1. Part D, secant of A is negative and cosecant of A is positive. So recall that these reciprocals have the same sign as their original values. So secant has the same sign as cosine. Cosecant has the same sign as sine. Hopefully that doesn't get too confusing with the word sine meaning two different things. So secant is negative wherever cosine is negative, which means quadrants 2 and 3. Cosecant is positive wherever sine is positive, so quadrants 1 and 2, which must mean that we're in quadrant 2. Finally, part E, cosecant of gamma is negative, while cotangent of gamma is also negative. So cosecant is negative wherever sine is negative, in quadrants 3 and 4. Cotangent is negative wherever tangent is negative, meaning quadrants 2 and 4. So gamma must be in quadrant 4.